Okay, guys, so we're going to cover chapter 14 this way. Chapter 14 is environmental health and toxicology. So we're still talking about the effects that the human population has on the planet. So these are the things that we're going to do. We're going to talk about toxic substances, how they study the effects of toxic substances, and how different areas of the world regulate substances that make their way into the market. So this is the case study. It's about BPA, or bisphenol A. It has been linked to a lot of really bad diseases like breast cancer and prostate cancer and heart disease. It's an additive that makes the coatings of metal cans. It's in dental sealants, and most common to you guys, it was found in plastic water bottles up until Erin was, probably one or two. That's when they first started advertising that plastic is BPA free. It makes the bottles less likely to shatter, so it makes them more shatter resistant. So how is it affecting us? 93%, that's a crazy statistic. 93% of Americans have BPA at detectable levels in their urine. So what does it do? There have been lots of studies done on animals to show the kinds of things that BPA can do, and they're listed there. The effects on men are different than the effects on women, which are different than the effects on kids. So it's what they call a hormone mimicker, right? So it mimics the structure of estrogen and can have some of those effects in animals with BPA in their systems. So the case study the article that I would have given you guys for this talks about the woman who discovered the link and how her findings were denied, and the government tried to cover it up. So yeah, that's a different topic of conversation. Places like Walmart and Toys R Us stopped carrying children's products with BPA. Canada doesn't allow it at all, and in the US it's restricted not to be used as often in kids' products. And a lot of the packaging or plastic bottles will say BPA free now, and that's what it means. BPA is this bisphenol A. So if you're into environmental science, but you're also into medicine or health fields, you can go into environmental health. So you can look at how environmental factors can influence our health or our quality of life. And some of those factors are natural and some of those factors are anthropogenic. If you don't know what that word means, get to know what that word means. That's human caused. All right. So there's 4 kinds of risks that we can talk about, hazards that we can talk about that have risks. So the first is a physical hazard. You can usually avoid those if you're careful, right? So UV radiation, natural disasters. So if you want to avoid the risk of ultraviolet radiation, you put on sunscreen. If you want to avoid the risk of a tsunami, you either don't live where tsunamis can happen, or if you don't really have a choice, you can have some kind of warning system. And they have those in the Pacific and the Indian Oceans now. Chemical hazards are synthetic chemicals plus natural toxins. So pharmaceuticals, disinfectants, pesticides, and venom are all examples of chemical hazards. Biological hazards. We understand biological hazards very clearly now. Okay, so it's interactions with other organisms like viruses, bacteria, insects, or parasites. We know what an infectious disease is. It's a disease that can be spread from person to person. And the organism that spreads, in many cases, that disease from person to person, or that starts that infection, is called a vector. Okay, and mosquitoes are a great example of a common vector for humans. There are a number of infectious diseases that you guys need to understand. Not so much the history of them, but where they come from and how they get transferred and what the pathogen is. Okay, so the plague is carried by organisms that have the plague bacteria. The original plague was carried by rats, and it's transferred to humans through the bite of an infected organism, so a rat bite or a flea bite from a rat, or through contact with contaminated fluids or tissues. Tuberculosis is a bacterial infection that affects the lungs, and that is transmittable by air, right? Or from bodily fluids of an infected person. So through coughing, sneezing, respiratory droplets. Malaria is a parasitic disease caused by bites from the infected mosquitoes. And commonly it's found in sub-Saharan Africa and in equatorial regions in the Western Hemisphere. So when I went to the Dominican Republic a couple years ago, I had a blood donation scheduled for like 2 days after I got back. And they denied me, they said, you can't donate blood because you were in the Dominican Republic. And I said, well, I didn't leave the resort. I didn't go into the jungles or anything. They said, nope, we're going to defer you for a year. So I wasn't able to donate blood for a year because I was in a malaria zone. They consider, the Caribbean and Central America and equatorial South America, they consider that to be a malaria zone. West Nile virus is something that happens here. Ooh, there's a typo. West Nile virus is transmitted to humans via bites from infected mosquitoes. Okay. Birds can get it as well. SARS, which is severe acute respiratory syndrome. It's a kind of pneumonia. It's transferred by inhaling, so you can inhale it, or you can get in contact with infected fluids like respiratory droplets and that kind of thing. MERS, or Middle East Respiratory Syndrome, is another viral respiratory syndrome that is transferred from animals to humans. Okay, probably in a similar way that COVID was transferred to the human population. SARS and MERS were big things, but not anywhere near as big as what COVID has been. Zika is another thing. Zika is caused by bites from infected mosquitoes, and it can also be sexually transmitted. So that was an interesting thing. Probably about 2 years ago when I was down in the Dominican Republic. There was a lot of discussion about Zika coming back and the impact it has on pregnant women and then their babies that are born. Cholera is a bacterial disease that's contracted from infected water. There was a cholera outbreak in London in the 1800s, and we're going to talk about that in a little bit. So those are some of the big diseases that you need to know how they're transmitted and the bacterial or viral nature of each disease. A cultural hazard is something that is a hazard because of our place where we live, what we do, or our socioeconomic status. Okay, so one example is choosing to smoke. Choosing to smoke is a behavioral choice. Hanging around people who smoke or vape, because smoking is not the thing anymore. Cigarettes are not the thing, it's the vape pens. Your diet, using drugs, and any hazards that you face in the workplace. You can choose to change your job. You can choose to move to another place. You can choose not to be around the people that do those kinds of things. So that's a cultural hazard. And those are the 4 kinds of hazards. So those were the infectious diseases that we talked about. There are non-infectious diseases. If you take a look at the non-infectious diseases that they develop without anything getting into you. Okay, so if you look at the pie chart on the left, okay, infectious disease is only accounts for about 17% of the deaths all over the planet. And if you look at the other 83%, yes, I did the math real quickly, 83%, 83% of the deaths on the planet are from non-infectious diseases. Okay, so people think, Zika and malaria and even COVID are big issues, and they are, and they're killing people. But most of the deaths on the planet are from non-infectious diseases, most of which is cardiovascular disease. Okay, And if you look at that wedge of the pie that's infectious, the bar graph on the right shows how that breaks down. Okay. So almost 3.25 million deaths a year come from respiratory infections like the flu and the pneumonia and stuff. Malaria is less than 500,000. AIDS is still over 1.5 million. And diarrheal diseases like cholera and dysentery are the second most common. Non-infectious diseases the impact of them can be lessened through making different choices. All right. So smoking rates have decreased in the last 25 years. Obesity rates have increased. All right. So lung cancer is less of a thing than it was 25 years ago. It still is a thing. It's what took my mom. But she also smoked since she was like 13 because it was the thing to do. But because obesity rates are higher, heart disease and type 2 diabetes have gone up. Okay. So that's the trend. Infectious diseases are a thing. They've been a thing, which we know, and that's how they spread. You guys know that. And you know how infectious diseases are passed. I mean, how infectious diseases ravage a body. The pathogen will use the human body as a host, and then it will reproduce. And then when there's enough virus built up or bacterium built up within the person, that person will cough or sneeze or vomit or, the other end. And then that viral material or bacterial material will be released into the air or the water. So that's why it's really important, to prevent the spread of COVID, to make sure that you're washing your hands, you're wearing your mask, all that stuff. Lots of ways that we can fight infectious diseases. The crazy thing is, scientists didn't really make the connection between disease and microorganisms until the late 1800s. So, there's a saying that says that most men in the Civil War who were injured, didn't die of their injuries. They died of infection. And that's true because they didn't understand that, cleaning the tools before you amputate a guy's leg after you just amputated another guy's leg would prevent the guy from dying. Okay. Then antibiotics and societal approaches, which helped to minimize the spread of disease after that. So indoor plumbing was a much better thing after the late 1800s into the early 1900s. We started sterilizing and treating drinking water, and then paying more attention to nutritious diets to help deal with any dietary deficiencies that could cause these viruses and bacteria to wreak havoc. So this is a diagram, a cartoon actually, that talks about the cholera epidemic in London in the late 1800s. So this is where they started to figure out that quarantining people who had a disease, who showed symptoms of a disease, was one way to stop it from spreading. So quarantining has been a thing since the 1800s, all right? And then looking to break that cycle. And it was really helpful in saving lots of lives during the cholera epidemic, but not before lots of people died as the result of cholera infections. Clean water and sanitation. We looked at this when we looked at the beginning of chapter 8, that National Geographic video. So that red is where less than 50% of the population have access to safe drinking water and sanitation. So India and most of sub-Saharan Africa are really big issues. Russia is not great, with only 50 to 75% of the population having adequate sanitation and water supply. So it's, 2020, this was done in 2018, and there's still a portion of the population that doesn't have it. And there are, countries around the world where we don't have data, right? I have the feeling New Zealand down here has pretty good access to sanitation and water. I forget. Ethiopia, I know what this one is. No, that's not Ethiopia. Oh my gosh, I can't remember what it's called. This one doesn't have that much adequate water supply. Is that Djibouti? No, that's not Djibouti. I forget what country that is. Oh, I'm so embarrassed. Okay. So infectious disease is still a concern. We're in the middle of an epidemic. So me telling you guys about this is not something you haven't already lived. These pathogens mutate, and the strains of these pathogens have slightly different genetics, which is a struggle. It's why vaccines and stuff are really difficult. When the virus or the bacterium mutates, it can change the genetics to the point that the vaccine won't work. And this is a big thing, right? We travel as a species because of airplanes and all that. We travel a lot more than we used to. So when we get on these planes in Europe, we can carry the disease with us unknowingly to other places. And that's, and a lot of commerce happens that way too. So that's where a lot of these, how this disease spread, Ebola spread in West Africa, and even COVID in 2020. So if you're into this stuff, you can study toxicology. All right. So toxicology is how poisonous substances affect humans or other organisms. Toxicity is the degree of harm caused by something called a toxicant. All right. Or a toxin. And anything can be a toxicant depending on the dose and the level of exposure. People can die. Water can be a toxicant, right? You've heard of the stories of hyponatremia where people drink too much water and they die. If you're into this, you can go into environmental toxicology, where you can look at how human chemicals released into the environment impact humans and the environment itself. All right. So there's environmental health hazards that exist indoors. All right. The two big ones are cigarette smoke and radon. All right. And they cause lung cancer. Radon is a thing around here because of the bedrock. It's a radioactive gas that comes up from the bedrock, and it tends to stay in your basement. Okay. So when we built my house in 2014, 2015, it was finally, we finally moved in 2015. We had to have a radon vent, right? So it vents air from inside of the basement to the outside. And you can actually get a radon kit to test your house to see how much radon your house has. And it can even be in your water because most of us have wells. Asbestos is a substance that was used as insulation, okay? And in ceiling tiles and in floor tiles, when they replaced the tile in the guidance office and the district office, they had to close the building because the tile had asbestos in it. And it causes something called asbestosis. If you've asbestosis, the asbestos mineral, it's actually a mineral, and I've identified it. It has little itty bitty tiny fibers. Okay. So when you breathe in those little itty bitty tiny fibers, it scars your lung tissue. And then if your lung tissue is scarred, it can't work. And that disease is called asbestosis. And lead is a heavy metal that can cause brain damage for the most part. Brain damage is the biggest issue. And a lot of the kids in Flint, Michigan, Flint decided a number of years ago to get its water for the municipal water supply from the Flint River instead of the Great Lakes. They changed their water supply. And the Flint River is full of lead. So lots of the kids who've been drinking water from the Flint River have some brain damage issues, okay? As a result of lead poisoning. It's a lot better than it was, for the most part around the country, but there are certain areas where lead concentrations are high. When you're a baby, when Aaron was a baby, they asked us some questions. Do you live in a house that was built before 1986? Well, no, we didn't, because lead-based paints were a thing in lots of houses built before 1986. And then leaded gasoline was a thing in the 1970s, and they phased that out in the 1970s. So once those things got phased out, then lead poisoning became less common. So this is a big thing. We've talked about this in almost every chapter that we've discussed. You have to do a cost-benefit analysis. You need to look at the risk of a substance compared to the reward of a substance, okay? Every chemical we use, there's potential human health risk. But is the benefit that that chemical is going to provide for the human population worth the risk? And toxicologists do studies to figure this out. So we're exposed to natural toxins, natural toxic substances, petroleum, radon gas, other things in the environment, but we're also exposed to synthetic or artificial man-made chemical substances like fertilizers and pesticides. So it's not just natural or it's not just man-made things. Both things can cause issues. Oodles of synthetic chemicals, we know that, okay? 100,000 chemicals in commerce, right? 8,700 food additives, right? 7,500 chemicals in 40,000 cosmetic products, and then 3,300 different human pharmaceutical chemicals. Some of the biggest chemicals, synthetic chemicals that we're exposed to are pesticides, and typically those pesticides are going to show up in areas where they're used, right? More so on farms, less so like in the cities, okay? So pesticides before the 1960s were sprayed over residential neighborhoods and public areas. And I'm going to show you guys a video during our next class about this. And Rachel Carson published a book called Silent Spring in 1962. And it was a huge hot button topic. She got death threats from her, publishing this. She was taken to court for defamation because she spoke out so strongly at how chemicals like DDT and other chemicals like dieldrin and things that you're going to see in a couple minutes, how harmful they were to people, okay, and then life in general. So the chemical industry really stood up to her, and that's where the death threats came from. But it was so widely accepted, and it caused such an alarm that DDT was eventually banned in the United States in the 1970s. Not everything that's toxic is synthetic. There are natural toxic things. We can't assume that all artificial substances are unhealthy and all natural substances are healthy, okay? That's an assumption. That's just something that we think, but it's not always the case. Toxic substances are in different forms, so these are good things to know. Carcinogens cause cancer. Mutagens cause mutations in DNA, and not every mutation is going to be negative, right? Some of the mutations, depending on the kind of mutation that it is, flashback to biology, could have little or no effect, but some of those mutations can cause diseases like cancer. Teratogens cause birth defects. Neurotoxins damage the nervous system. Heavy metals are an example, right? Allergens overactivate the immune system, okay? So asthma is a thing. Asthma is caused by an allergen. If you have a peanut allergy or a tree nut allergy or anything like that, that is caused by an allergen. All right. And pathway inhibitors block a step in a biochemical pathway. All right. So cyanide is an example of a pathway inhibitor. Cyanide interrupts the electron transport chain, okay, in respiration in the mitochondria. So that's why cyanide kills you. Endocrine disruptors. This is big. You guys need to know what endocrine disruptors are. They frequently mimic hormones, okay? They either block the hormone from working or they break it down so there's less hormone in the body, or they mimic its effect, okay? So BPA mimics estrogen. All right. So normal hormone binding, let's say this is estrogen. There's a hormone outside the cell, and then there's a hormone receptor in the cell membrane. So when this little set hooks up, it causes this response, okay? When you move a hormone mimicker into a system like BPA, right? There's less hormone in the body, right? So there's less natural hormone, but it seems like you have more hormone. So you cause this reaction to happen again and again and again. Okay. So that's where you have some of the issues that we talked about with BPA, particularly in men. It's not a good thing. Phthalates are something else. Phthalates make plastic soft, and they are fragrance enhancers in some cosmetics. Phthalates, if you look at nail polish these days, it says it's phthalate free. And these soft things also say they're phthalate free. That's hard to say. Phthalate free. Okay. They're endocrine disruptors too. So they have wonderful side effects. How sensitive you are to a toxin is going to depend on your genetics, your health, your gender, and your age. The younger or older you are, typically the more sensitive you are to a toxin. And how dangerous a toxin is to you depends on whether your exposure is acute. So it's a high exposure over a short amount of time, or chronic, a low exposure over a long period of time. We're going to skip that. So, toxic substances aren't evenly spread everywhere. And if you think about salt in the ocean, this makes sense too. The water in rivers isn't salty, but there's salt in it. So if you have all of the salt from all of the rivers in all of the world dumping into the ocean, the water evaporates out, but the salt doesn't. So that water the salt is going to concentrate in the ocean water. And this happens too with other toxic substances, not just salt. So as water runs off from land, like we talked about in the last chapter, any toxicants or toxins or pollution that's on the surface is going to run into that water and concentrate them in that creek or that stream or that lake. Okay, because you have that toxicant coming in from many different sources. Wastewater treatment plants add toxins, pharmaceuticals, and detoxification products to waterways. The water, when we get to that point, you'll see the water that comes out of a wastewater treatment plant has to be tested many, many times before it's released. And chemicals that are in the soil, if they're on the top of the soil, they can leach into groundwater and then contaminate drinking water supplies. So water is a main source of toxic chemicals as well. And you know that from, a couple years ago when our water was contaminated and we had to have the water coolers. That's cool. Some toxicants persist in the environment. Some don't break down as easily. Okay. So those that don't break down as easily, that are resistant, they are persistent, they're going to cause more issues. Okay. Sometimes those toxicants can break down into simpler compounds, which could either be less harmful or more harmful or as harmful as the original substance. This is a big idea that you need to make sure you understand. It's this idea of bioaccumulation. And I think we talked about it before. If we did, that's good. We're going to talk about it again. So things that are fat or oil soluble are absorbed and stored in body tissues. So some things like lead or mercury don't metabolize out. All right. They stay in an organism's body. So when that happens, bioaccumulation will occur. So bioaccumulation means that the concentration of the substance in the tissue is higher than that of the environment. All right. So there's more inside the body than there is outside. And that stuff, that material, that toxic material will transfer up the food chain. All right. So this is bioaccumulation, okay, of DDT. All right. If you look at what's in the water, okay, there's this many parts per million of DDT in the water. But that zooplankton, as they do their thing, they take in more than one water molecule. So what happens is that it bioaccumulates. There's more DDT in the zooplankton than there is in the water. And that happens all the way up the food chain till you get to the osprey at the top of the food chain, right? So each zooplankton takes in a bunch of water. Each small fish eats a bunch of zooplankton. Each large fish eats a bunch of small fish which have eaten a bunch of zooplankton. And each osprey eats a bunch of large fish, which have eaten a bunch of small fish, which have eaten a bunch of zooplankton. Okay? So what winds up happening is that as these predators ingest more and more prey, the concentration of these toxins is ridiculous. It goes way, way up. So the difference between the amount of DDT in the water compared to the amount of DDT in the osprey is roughly 8 million times. There's 8 million times more DDT in the osprey than there is in the water. And this was a huge issue for North American birds of prey. So the bald eagle, the osprey, the golden eagle, they would, eat these fish and have all this DDT biomagnified in their body. They would lay their eggs, and when they would go to sit on their shells would be so thin from all the DDT in their body that they would sit on the eggs and they would crack. So the bald eagle is now successfully not endangered anymore, in large part due to the fact that DDT is banned. We're going to skip that one. Okay. So we're talking about how all of these toxins affect animals, but we're kind of interested in how these toxins affect humans too. So we can take a look at individual patients and use something called the case history approach. So we can understand disease and understand how individual people are handling the disease, but it doesn't tell us much about the population level. So in order to do that, we have to do what they call epidemiological studies. Okay. It's a large scale comparison over longer periods of time, right? And looking for some of the effects that are more long-term rather than those that are immediate. And they're doing epidemiological studies now related to COVID. We have a county epidemiologist, and the superintendents of the high schools in Hunterdon County are in regular contact with the county epidemiologist to look at how COVID-19 is spreading right now. Okay, so they take a look at how they got to where we are, but in a lot of cases, it's hard to predict what's coming because there are so many external factors that influence the spread of a disease. So if we're going to establish causation, right, if we're going to link a cause and an effect to a toxin or what have you, we need to do studies. We need to use subjects, and ethically, we're not using human subjects. So this is where animals are frequently used to test the spreads of disease. Okay, and we use animals, mice, rats, rabbits frequently because their bodies function similarly to ours. So what they do is what they call a dose response analysis. Okay. So you give test subjects measured doses of a toxin, okay, and then you measure the effects of those concentrations on animals in those varying concentrations. So the dose is the amount of substance that the animal receives, and the response is the effect of that dose, the response to that dose, okay, the magnitude of toxic effects. And then you can plot it, and what you get is called a dose response curve. And this is what they call a dose response curve. It's a linear dose response curve. And you can use the dose response curve to get something called the LD50, the lethal dose 50, which means It's the amount of substance needed to kill half the population of study animals. Okay. You need to know what the LD50 is. The amount of substance needed to kill half the population of study animals. So you find 50% on the percentage of the test population infected. You drag it out to the dose response curve, and you drop it down. Okay. And that's the dose. The higher the LD50, the higher the dose it takes to kill 50% of the study animals, the lower the toxicity. This is so huge. The lower the LD50, the lower the dose at which 50% of the animals die, means it's a higher toxicity. All right. Now that's for lethal substances. You can look at non-lethal toxicants and get something called an effective dose 50 or an ED50, where you see marked effects on 50% of the population rather than the death of 50% of the population. Sometimes the animal's body can metabolize or excrete a toxicant at low doses. So you get what they call a dose response curve with a threshold. All right. So when you see this line, the dose response curve at 0, up until this point in terms of the dosage, the body is able to metabolize it and it doesn't become toxic. After this point, you start to see a reaction. Okay, you start to see a response. So again, you read it the same way. Take the 50%, take it over to the dose response curve, drop it down, and that's where your LD50 is. You're going to see these things again. All right. So when you've got stuff like endocrine or hormone disruptors, you can see where the reaction will peak, but then it's going to drop off. And that's because you've overwhelmed the system. Okay. You don't have the ability to process any more of that material, all right, that you can still get an LD50 out of it, but these are way less common. If you mix toxicants together, like the Joker did in the first Batman movie from the late 1980s, they can either cancel each other out or they can exacerbate the reaction, and those are synergistic effects. Okay, it's really hard to figure out what's causing a reaction when you have these synergistic effects going on. Okay, we will talk about this in class. Darn it. In everything we do, there's risk, okay? And risk is measured in terms of probability, which is a quantitative description of the likelihood of a certain outcome, all right? If something harmful will come out of it, that is the risk. Okay, the probability that something harmful is going to happen is the risk. We try to minimize risk, okay? But things that we think are high risk really aren't that high risk, okay? So we have, as a race, as a species, a 1 in 7 chance to get heart disease and cancer, okay? Those are really rotten odds. But, okay, people are terrified in a lot of cases of getting on a plane when it crashes and thinking it's going to crash. 1 in almost 10,000. Drowning in submersion, right? So, your car runs off the road into the river. Okay, that's a 1 in almost 1,200 chance versus 1 in 7, okay? So people worry about small risks, but don't think about doing things that pose high risks, okay? That's just something to think about. All right, we're going to skip that. This just shows how policy gets made. We're not going to dwell on that either. So in the U.S., managing risk is handled by the FDA, the Food and Drug Administration, the EPA, the Environmental Protection Agency, and the CDC, the Centers for Disease Control. All right. So they have to do a cost-benefit analysis. Yes, BPA is causing issues, but what's the cost of finding a replacement for BPA? Well, it's going to raise the cost of production because BPA is cheap. So then if we replace BPA, production costs are going to go up, and that's going to be passed on to the consumers. And is it something that the consumers are willing to accept? Is that an acceptable cost for the benefit of the replacement for BPA? That's the question that they have to ask. Okay, so these are two different ways that products can get to market, all right? So we'll look at the two of them, and the next couple of slides show them. So there's the innocent until proven guilty approach, and then there's the precautionary principle approach. So we've got two products trying to come to market, and we look at the stuff on the left, the innocent until proven guilty approach, right? So there's some initial research and development. There's pre-market testing going on and in the second block. And then that testing says, okay, both products are good to go to market. So they go out into the market. Consumers start to use those products. One of those products starts to harm people. People get sick. People have allergic reactions, okay? And now is the point where we start to test a little bit harder. So post-market testing, industry, government, academic scientists. So they do more rigorous testing after a problem has happened. And then those test results say that this blue product is unsafe. So the blue product is recalled, it's removed from the market, and what's left, the purple product, is safe to use. Okay, that's one approach. The other approach is the precautionary principle. So you have the same two products trying to get to market. They test, and test before the products hit the market. They discover in that pre-market testing that that blue product is not safe. So the blue product never makes it to market. The purple product makes it. It has a minimal impact on human health. There's a little bit of additional testing, but there's nothing to say that that purple product is unsafe. So the purple product stays on the market in both cases, but the blue product makes it to market on the left in the innocent until proven guilty approach. On the right, it never makes it to the market. Okay? So basically, the innocent until proven guilty approach says that substances are harmless until they're shown to be harmful. That's good because it gets new products to market quickly, right? It doesn't inhibit the business process. But the downside of that is it can put dangerous substances into use without testing. The precautionary principle assumes that everything is harmful until it's proven not to be. Okay. In this way, less harmful substances, there's less overall damage that when a new product is released. Okay. But the downside of that is, there's less profit to be had and technological advancement doesn't happen as quickly. So one of these is the European way and one of these is the American way. So I'm going to pause for about 10 seconds and let you guys figure out which way is which. European nations do the precautionary principle, and the U.S. follows innocent until proven guilty. And there are different agencies that track the health issues. FDA monitors food, drug, cosmetics, drugs, and medical devices. EPA's pesticides, and OSHA regulates hazards in the workplace. You guys probably aren't surprised by that. There are two different ways of regulating chemicals. One is REACH, which is the European Union, and the TSCA is the United States. So again, this is just a diagram that furthers the evidence that we use the innocent until proven guilty approach, and Europe uses the precautionary principle approach. We've tried to deal with chemical pollution with international treaties. The Stockholm Convention was in 2004, and it was on persistent organic pollutants, or POPs, right? POPs are toxic chemicals that wind up persisting in the environment. They're fat soluble, they bioaccumulate, they biomagnify, they are around for a really long time, okay? And there are what they call the dirty dozen. Okay, the Stockholm Convention wants to get rid of these, the dirty dozen, and there they are: aldrin, chlordane, DDT, dieldrin, dioxin, endrin, furans, heptachlor, hexachlorobenzene, Mirex, and PCBs, and toxaphene. Okay, and in A Silent Spring, Rachel Carson basically goes to war against the chemical companies, Dow Chemical and that kind of thing, DuPont Chemical, about these. Okay, so that's a little bit about toxicity and human impacts of it. And when we get together next class, I'll pull the most important stuff and talk about it a little deeper.